So we may learn on the lateral earth pressure on retaining wall due to the effect of the dynamic load. Okay. However, for the brace cut, okay, it is based on the static load only. Okay. So you may learn on how to determine the stress, okay, acting on the brace cut. Okay. It is similar with the lateral earth pressure topic. Okay. However, we not discuss on the dynamic loads. Okay. So the increase of lateral earth pressure during earthquake induce sliding or tilting to the retaining structure. The majority of case histories of failure reported in the literature now concerns on waterfront structures such as quay walls and bridge abutment. Okay, so this is the main concern on the lateral earth pressure or lateral retaining structure. Sorry, on the retaining structure due to the earthquake effect. Okay. So, based on the literature, okay, most of the concerns is more related to the harbour area, okay, where the more concern on the waterfront, okay. So, what is the waterfront? Okay, so this is example of the waterfront, okay, or quay walls, okay. So, it normally construct on the harbour uh, to allow for the ship, okay, to move near to to the to the to the side of the harbour, okay, in order to upload or loading the uh, container, okay. Okay, so some of the example of failure and lateral movement of quay wall, the earthquake are given in table 1, okay, as I shown previously. Okay, Sid and Whitman have suggested that some of this failure may have been due to several reasons, okay, such as the increase of lateral earth pressure behind the wall, reduction of water pressure at the front of the wall, okay, and the last one is due to the liquefaction of the backfill material. Okay. So this is what has been observed by Sid and Whitman, okay, due to the earthquake event. Okay, a comprehensive review on the dynamic lateral earth pressure studies conclude that the theory can be divided into three broad categories. Okay, which first one is the fully plastic solution. A solution based on elastic wave theory, and the last one is solution based on elastoplastic nonlinear theory. Okay. So because of the complex of soil structure interaction during the earthquake, the lateral earth pressure theory based on the fully plastic solutions, okay, which is widely used by most of the design engineer, is detailed in this topic. Okay. So they have three types of theory related to the lateral earth pressure. Okay. So however, due to the complex of the soil structure interaction, okay, we may focus only on the fully plastic solution, okay, which is the way that normally we use when we deal with the static load problems. Okay. So in that case, we may review again, okay, the static lateral earth pressure equation, and then there will be some improvement has been made, okay, to cater for the what we call as the dynamic loads. Okay. So in earthquake engineering, to analyze the seismic response of the soil embankment and slopes, simply adding a permanent body force representing the earthquake shaking to a static limit equilibrium analysis. Okay. So in a way to improvise the static equation. Okay, so they add some element, okay, which is called as a permanent body force, okay, to represent the earthquake shaking, okay, to the static limit equilibrium analysis. Okay, so okay, this is um, the list of the failure and movement of quay walls. Okay, so most of the event, okay, has been recorded in Japan. Okay, so for example, due to the earthquake Kitaizu, Shizuoka, Tonaika, Naika, Tokachi, Chioki, okay, and there are one happened in Chile, okay, and the other one is happened in the last one is happened in also in Japan. Okay, okay, so now we look on the theory of the lateral earth pressure. Okay, analysis determination of lateral earth pressure are necessary to design retaining wall or retaining structure. There are three categories of earth pressure. Okay, the first one is the earth pressure at rest, which is elastic equilibrium with no lateral strain taking place. Okay, so in this case, we assume that the soil, that the wall is stable. Okay, so there are no movement, so that they define as no lateral strain taking place. Okay, so normally in design, we are more interested on the active of pressure. Okay, which is we assume that the soil have a lateral expansion. Okay, so it meet the plastic equilibrium. Okay, where it reach the failure state. Okay, so there will be two type of plastic equilibrium for the lateral stress. The first one is the active earth pressure, and the second one is the passive earth pressure. Okay, where the active earth pressure is more related to the expansion, while for the passive earth pressure is more related to the compression. Okay, so this is illustration or diagram, okay, to um, show uh, how the stress, okay, how the lateral stress acting on the soil for the at rest and acting on the retaining structure for the active and for the passive. Okay. So first we need to determine what is the vertical or effective vertical stress. Okay, then we may multiply with the K naught value for at rest. While for the active, we need to multiply with the Ka, and for the passive, we need to multiply with the Kp. Okay, lateral pressure. Okay, for the at rest, okay, we may use this formula. So K naught, okay, we may obtain from the phi value, which is 1 minus sine phi. Okay, there will be no there will be no use of the cohesion C, okay, because it is still under the elastic conditions. Okay, it doesn't reach the failure or the plastic, so there will be no C value for this at rest. Okay, and then for the active and passive, okay, we may discuss on the Rankine theory and also on the column theory. Okay, for the Rankine theory, the assumption has been made by the Rankine where there is no addition of friction between wall and soil. Okay, so it assumes that the wall is smooth. Okay, while for the column assume that failure occur in the form of which and that friction occurs between wall and soil. Okay, so uh, the friction between wall and soil is uh, shown, okay, or it's been calculated based on the sigma value. Okay, normally we may consider 2/3 from the phi value. Okay, so it should be less than the phi value for the friction between wall and soil. Okay. Failure is assumed to occur in the form of sliding wedge along a failure plane. Okay, so this is the type of failure. Okay, the first one we may consider as a passive, while this one is the active. Okay, so by assuming this is the what we call is the degree of the failure. Okay, so we may use this value, okay, to derive for the equation for the Kp and also for the Ka. The direction of resultant pressure is parallel to the backfill and act to the 1/3 from the wall base. Okay. Okay. For example, if this is what we call as a one layer of soil. Okay. So when we calculate for the stress or for the effective stress, okay, for this single layer of soil, okay, so it will show a linear increment, okay, with the depth. Okay. So by using the moment concept, okay, let's say this is the base. So then the direction of the resultant pressure, okay, is 1/3, okay, from the what we call as from the base. Okay, because this is based on the moment concept, okay, to identify the moment arm for a triangular shape. Okay, so it is a 1/3 from the base. So then we multiply with the P. Okay, so in order to get the P, okay, for example, this is a H, okay, and this is the pressure. Okay. So to gain the pressure at this level, okay, so the unit weight of the soil, okay, times with the H, okay, and then we may convert to the what we call as to the lateral pressure. Okay, then we may multiply with the Kp, for example, Ka, for example. Okay, so the P, okay, is the area of this triangular shape. Okay, so the area for a triangular shape is the half, okay, times gamma, unit weight of the soil, okay, times H square, and then times Ka for the active lateral stress. Okay. So this is for a single layer of soil. Okay. However, if we did a multi-layer of soil, okay, so there will be another discussion where we need to identify what is the pressure acting uh, on any level, okay, where it have any difference of soil properties. Okay. However, for this topic, we only discuss on a multi-layer of soil. Sorry, a single layer of soil. Okay. Okay. So in 1776, the column derived an equation for active earth pressure on the retaining wall due to a dry cohesionless backfill. Okay, so this is equation, okay, that's been proposed by column where he includes, okay, the friction between wall and soil. Okay. So in addition, okay, so he also include, okay, the what we call as the I, which is the slope of the backfill with respect to the horizontal. Okay. So for example, this it is the backfill has a certain slope. Okay. So it is not a flat backfill. Okay. So we need to consider the value of the I, and also, okay, what we call as the retaining structure. It is not 90 degree, okay, towards the horizontal. So it has a certain degree where they call as a beta slope at the backfill of the wall with respect to the vertical. Okay. So if respect to the vertical, so 0 degree for what we call for a straight cut slope, for a straight cut of retaining structure. However, the column has include, okay, the effect of the slope of the backfill of the wall with respect to the vertical direction. Okay. Okay. So then we may use this equation, okay, to calculate for the KA. Okay. And okay, this is the what we call as the equation for a single layer of soil, okay, to determine the active um, uh, lateral pressure. Okay. So for the column, okay, so the total thrust or the PA, okay, the direction of the PA, okay, it is not as what we call it perpendicular, okay, to the retaining structure. Okay, so for example, if it's perpendicular, it will be like this. Okay, so it may have a certain degree, okay, due to the friction between wall and soil. Okay, so we need to include the sigma value, okay, in the to determine the the direction of the PA. Okay. Okay, so this is for the column equation. Okay, in the actual design of retaining wall, okay, the value of the wall friction sigma is assumed to be between half of the phi and two-thirds of the phi. Okay, so means that it is less than the phi value. Okay. So the active earth pressure coefficient for various value of phi, I, and beta with a sigma range from 0 to 25 and two-thirds from the phi, okay, are given in table 8.2 and 8.3. Okay. So for example, okay, if uh, we doesn't want to use this equation, okay, so then we may use this table, okay, where we can get a a straightforward value for the KA, okay, by knowing the value for the P, for example. However, this is been restricted to the beta, so means that the wall, sorry, the wall is straight to the vertical, to the horizontal, okay, and and the backfill is slope, or the backfill is flat, okay, because the I is equal to 0, and the beta is equal to 0. Okay, then we can identify what will be the Ka value. Okay, and the sigma, for example, if the sigma is being provided, so we can just guess what will be the Ka value. Okay, so let's say we are given with the sigma equal to 2/3 of the phi. Okay, then we can use this table. Okay, where uh, we have I, okay, here, and also the degree, and also the beta value. Okay, so for example, for the beta, okay, this is the beta. Okay, and there are some degree of the slope at the backfield. Okay, so for example, if 20, if we refer to 20, okay, so then we can estimate the Ka value, okay, based on the different phi value as well. Okay, let's say the phi value is equal to 30. Okay, so then we choose 30 here. Okay, with the I equal to 20. Okay, and also the beta is equal to, for example, 10. So the value for the Ka is 0.5403. Okay, so if you want to verify the result, okay, so you can use this equation. Okay, okay. However, this table, okay, is should be used when the data is equal to 2/3 of phi. Okay, okay, okay. So that is for the static equation for the lateral stress. Okay, so now we look on the Monologic Okabe, okay, active earth pressure theory, where he has what we call as improvised, okay, the static column active earth pressure equation, okay, to um, cater for the earthquake event. Okay, so column active earth pressure equation, it can be modified to take into account the vertical and the horizontal coefficient of acceleration induced by an earthquake. Okay, so this is referred to as the Monologic Okabe analysis. Okay, so in 2009, in 1929, and also in 1926. Okay, so the latest one is 1929. Okay, so then Monologic Okabe has provide the solutions. Okay, based on this static approach, or based on the column active pressure. Okay, so the mononomic Okabe solution is based on the following assumption. The failure in soil take place along a plane such as BC shown in figure 8.2. Okay, okay, the same concept with uh, what we call as uh, the the column or the rankine. Okay, so this is the B and C line. Okay, so this is the assume failure or assume which failure. The movement of the wall is sufficient to produce minimum active pressure. Okay, the shear strength of the dry cohesionless soil can be given by the equation. Okay, S equal to sigma phi tangent sigma prime tangent phi. Okay, where sigma prime is the effective stress and S is the shear strength. Okay. At failure, full shear strength along the failure plane is mobilized, okay, which is the plane BC. Okay, the soil behind the retaining wall behave as a rigid body. Okay, so this is assumption made by what we call as Monologic Okabe approach, which is similar with the static one. So that's why they only improvise the static equation, okay, to cater for the earthquake event. Okay. So, okay, figure 8.2 show the force considered in mononomial Okabe solutions. Okay. So they include what we call as the KV, W and KHW. Okay. So this is more related to the what we call as the horizontal and vertical acceleration force. Okay. The line AB is the back face of the retaining wall, and ABC is the which will fail. Okay, the force on the failure, which per unit length of the wall are width of the which W. Okay, so active force. Okay, so they include the E in the notation to represent the earthquake. Okay, so resultant of shear and normal force along the failure plane, which is the F. Then they introduce the KHW and KBW, which is the initial force in the horizontal and vertical direction, respectively, where KH is the horizontal component of earthquake acceleration over acceleration due to gravity, and KV is the vertical component of earthquake acceleration over the G. Okay, so they improvise the static by introduce the KVW and KHW. Okay. So then they gain the PAE. Okay. So this is the force polygon. Okay, which is they are additional of this KVH and also KHW. Okay, means that previously the force polygon only have F, W and P, A. Okay, however, when they introduce the earthquake event in the equations, so they have the PAE, KVH, KVW and KHW. Okay. So the active force determined by the wedge analysis described here may be expressed as, okay, so this is the equation where they include the 1 minus KV. Okay. Where KAE is the active of pressure coefficient with the earthquake effect. Okay, so later on, the column KA has been improvised by introducing the theta. Okay, so this is the theta value or equation. Okay, that we need to use to get the KAE, and then from there we include in the equation to get the PAE. Okay. So for the active force condition PAE, the angle alpha that the soil which ABC located behind the retaining wall, okay, figure 8.2. Okay, this one. Okay, so that is the alpha mixed with the horizontal. Okay, for KB not KB equal to 0, beta equal to 0, I equal to 0, phi equal to 30, and sigma is delta is equal to 0 and 220 is shown in figure 8.3. Okay, so then, okay, to estimate what we call as the value for the sorry, to estimate the value for the KAE, okay. So we can use the table of 8.4, okay, which is the same approach that we have learned from the previous table for the static one to get the KA. Okay? So this is the table that we may use to determine the KAE, or otherwise we may use what we call as the table, sorry, this equation. Okay. Okay. Uh, okay, sorry, this is to determine the KAE, okay, and the angle that we want to determine for the alpha, okay, so we may use this figure 8.3, okay, okay, for the alpha. So actually the alpha doesn't really important, okay, if we rely on this equation, okay. It just to get the alpha value, okay, to know what would be the degree of the which uh, failure. Okay, but we may look what is the use of the alpha later on. Okay. Then table 8.5 give the value of KAE for various value of the phi, theta, I and KH with KV and beta is equal to 0. Okay, so this is the condition, okay, when we want to use the table 8.4, okay, to obtain the KAE. Okay. Okay, so this is just mm, that we need to consider, okay, when we want to use the what we call as the approach by Monologic Okabe. Okay, so considering the active force relation given, the term sine phi minus theta minus I has some important implication. Okay, so first, if the phi minus theta minus I less than 0, okay, which is negative, no real solution of KAE is possible. Okay, so means that the phi is very important. Okay, if the phi is negative, so there will be no, if the end product is negative, so no real solution KE is possible. Okay, so means that the theta and I, okay, so where's the theta, okay, so means that the theta from this equation, okay, um, should not greater than the value of the, sorry, the value of the value of the phi, okay, and also if and also the I, okay, should not greater than the value of the phi. Okay, so physically it implies that an equilibrium condition will not exist. Okay, hence for stability, the limiting slope of the backfield may be given by I less than the phi value. Okay, we cannot control the theta because the theta is based on what we call as based on the earthquake condition. Okay. However, we can control the I. Okay. So means that the I is the slope at the backfield. Okay. So we may reduce the I. Okay. So that it will not reach the negative value when we calculate for the phi minus theta and minus I. Okay. So for no earthquake condition, okay, which is the theta, okay, so this is on the static, okay. For stability, give the familiar relation of which is the I, okay, should less than the phi minus theta, okay. So secondly, for horizontal backfill, okay, which is I is equal to 0, okay. So definitely the phi should be greater than the theta, okay. So we need to make sure that uh, the phi should greater than the theta and also the I. Okay. So if the phi is less than theta and phi, and the theta and I, so we cannot use the KAE, and we cannot gain the KE value, okay, because it will provide a negative value. Okay. So it's very important, okay, to play around with the I, okay, in order to increase the phi value. So we need to make sure that the phi or the compaction should be as good as uh, what is been obtained in the lab, okay, which is should reach 90% from the compaction effort, which is from the modified, which is from the proto test, okay, to gain a high degree of phi value. Okay. Okay. So since theta, which is the equation that we consider, okay. So for stability, combining result in KH, okay, less than 1 minus KV tangent phi, okay. Hence, the critical value of the horizontal acceleration, okay, can be defined as in figure 8.4. Okay, so this is how we uh, identify the critical KH value, okay, based on the KV and also based on the soil friction angle. Okay, okay. So this is by using a chart, okay. Okay, the previous one that we learned is by using the equation, okay, to get the PAE. Okay, then there will be another methods, okay, that been provided by Arango. Okay, this guy has been provide another approach, okay, by using a chart, okay, to get the PA value, okay, PAE value, okay, by using a chart, okay. So this is the equation for the static, okay, while this is the equation for the dynamic, okay. So this is what we learn, which is the half times gamma times h square times Ka, okay. So then he has introduced, okay, this sub equation, okay, which is the AC is equal to Ka cos square beta, okay. And then the Arango also has produced this KAE, okay, by introducing this equation as well. Okay, okay. So a slight as the same with the one that I have discussed before. Okay, when they produce they introduce the theta, okay, in the normal equation of the static to determine the KAE. Okay. So then for the I prime is equal to I plus theta and B prime which is equal to B plus theta. So then they simplify the equation, okay, by introducing the I and the beta prime. Okay. So the preceding equation is similar to equation 8.13 except for that there is I prime and beta prime, okay, are used in place of I and beta, okay. So it means that this equation, okay, actually same with the equation of this one, okay. Thus it can be said that AM is equal to AC I prime B prime and KA I prime beta prime cos square beta prime. Okay, so the active earth pressure PAE can now be expressed as, okay, so this is the new equation, okay, where they have do some modification, then later on they come up with the P asterisk. Okay, so this is the P asterisk cos square beta prime over cos theta cos square beta. Wait a minute. Sorry. Okay. So then they come up with this procedure. Okay. I will share with you one example. Okay, on how to use this procedure. Okay. So in order to calculate PAE, okay, one needs to follow this step. Okay, first calculate the I prime. Okay, and then calculate the beta prime. Okay, so this is the equation of the I prime and beta prime. Okay, with known value of phi, delta, I and beta prime, calculate Ka, okay, from table 8.2, 8.3 or other available chart. Okay, so then we may use this sorry, okay, this one either 8.3 or sorry 8.3, okay, to get the value for the Ka, or 8.2. Okay, where is 8.2? Okay, sorry, 8.2 and point 8, sorry, 8.2 and 8.3 to get the Ka. Okay, so Ka is the for the static one. Okay. Okay. So then calculate for the Pa as equal to, okay, this is the normal equation, half times unit weight times h square times Ka. Okay. So then calculate the 1 minus Kv. Okay. So the next is calculate the asterisk P. Okay. So once we have already got all the value, okay, which is the PA, I prime, beta prime, okay, 1 minus Kv, and also the asterisk P. So then we can calculate for the PAE. Okay. So for convenience, some typical value of asterisk P are plotted in figure 8.5. Okay. So either we use this equation, okay, or we may use this, what we call as this figure, okay, to determine the asterisk P. Okay. Okay, so this is the procedure that made by Aragon, okay, to determine the PAE value. Okay. Okay, so now we look for one example here. Okay, so it's very easy to understand. Okay, so the one that we have discussed is more related to the how they develop the equation. Okay, So now we use the procedure, okay, to determine what will be the PAE. Okay. So okay, this is the problems figure 8.2. Okay. So if beta is equal to 0, okay, so this is 0, I is equal to 0, okay, I is equal to 0, P is equal to 36, delta is equal to 18, H is equal to 4.5, and unit weight is equal to 70.6, kV 0.2, KH 0.3, determine the active force per unit length of the wall. Okay. So the first procedure, okay, that based on the PAE, is based on this procedure, okay. So we need to calculate for the I and also the beta prime, okay. So the equation of the I prime and beta prime, okay. So need to refer to the I plus theta and beta plus theta, okay. So the theta we can get from this equation, okay. However, I have put in this example, okay, the procedure first is to calculate for the theta, okay, which is the tangent, a tangent KH over 1 minus KB, okay. So then we gain 20.56, where the KH is equal to 0.3, KB is equal to 0.2. Okay. Then we may calculate for the I prime and beta prime, okay, which is the I in our case is equal to 0 and beta is also equal to 0. Okay, so the I prime and beta prime is equal to 20.56 degree. Okay. So the next is to determine the KA. Okay, so to get the KA, okay, either we use this equation, okay, or we may use the what we call as the table 8.2 or table 8.3. Okay. So for example, if we use this equation, okay, so we need to put all the value, okay, then later on we can get the value of the KA, which is equal to 0.583. Okay. So now we look on the table 8.2 or 8.3. Okay. So we have here beta is equal to 0, I is equal to 0, P is equal to 36. Okay. So I need to check, does the sigma is equal to 2/3 of the phi or not. So 2 times 36 over 3, 24. So the delta is not 2/3. Okay, so we may use the equal, we need to use, for example, we need to use the table 8.2. Okay, so now we check 8.2 table. Okay, okay. So the degree of the phi is equal to, what the value of the phi? The phi is equal to 36, 36. Okay, 36. Okay, 36. Okay, this is 36. Okay. The beta and I is equal to 0. Okay. Okay, however, the what we call the sigma is equal to 18, 18. Okay. So it's very difficult to get the strict value unless we do the interpolation. Okay. Which is 15 is equal to 0 0.2379, 18 is equal to X, okay, and 20 is equal to 0.2354, okay. So by doing this interpolation, we can get the X value, okay. So however, the example show the use of the equation to get the value for the KA. So the value of KA is equal to 0.583. Okay. So if you have time, so you can use the chart or you can use that table, okay, to determine the KA value. Okay. So we already have the KA. Okay. Then we need to calculate for the PA. Okay, which is half times gamma times h square times Ka. So from there, we obtain 103.89. So that is for the PA. Okay. So the next is to calculate for the 1 minus KV. So it's very straightforward. Okay. 1 minus KV, we obtain 0.8. Okay. So later on, we need to determine the asterisk P. Okay. So the asterisk P formula is here. Okay. Cos square beta prime over cos theta cos square beta. Or we can use this figure to determine the asterisk P. Okay. So the asterisk P, okay, by using the formula is equal to 0.9363. Okay. So we look on the this value. Okay. So with the theta is equal to, what is the theta here? Theta is equal to theta, what is the 20? Okay, theta is 20.5, 20.56. Okay, approximately here, and the beta is equal to 0. Okay, so then we can estimate the value of the, what we call as of the asterisk P. Okay. So by the calculation, we obtain 0.9363. Okay, by looking on this graph, we can consider around 0.95 something, 0.95, 0.94. Okay. So that is the asterisk P. Okay. The last is to calculate for the PAE. Okay, we already have PA, we already have 1 minus KB, and also we have the asterisk P. Okay. So then 103.89, okay, times 1 minus 0.2, and then times with the asterisk P. So the value for the lateral stress, active lateral stress under dynamic loads is equal to 77.81. Okay, so that is the lateral stress, okay, due to the dynamic load, by using the Monologic Okabe and improvised by Aragon. Okay. So the effect of the various parameter on the value of the active earth pressure coefficient. Okay, so this is uh, the relation, okay, based on the effect of the wall friction angle. Okay, so the effect of the wall friction angle on the active earth pressure coefficient is rather small. Okay, so there are no slightly difference. Okay, if the friction between the wall increase from 0 to the maximum two-third of the P. Okay. So then they also look on the effect of the soil friction angle. Okay. So from the plot, it means seen that for KV is equal to 0, okay, this is the KV value. KH, when the case is equal to 0, okay, KAE under the 30 fee value is about 35% higher than the KAE at 40 fee value at the fee of 40. Okay, so if the fee of 45, so it will be increased near to 40%. Okay, here's a small error in the assumption of the soil friction angle could lead to a large error in the estimation of PAE. Okay, so means that we need to use uh we need to determine the correct P value to be used in the PAE calculation. So that is for the soil friction angle. Then what will be effect of the backfill? Okay. They increase the I value. Okay. So note that the KE sharply increase with the increase of the slope of the backfill. Okay. So means that if we increase the degree of the slope at the backfill, so the lateral earth pressure will become higher. So it's better for us to have a flat backfill at the back. Okay, so that is for the what we call as the mononobe Okabe. Okay, so we take a rest for 5 minutes and then we may continue for the another approach by using a graphical methods. Okay.
Thank you, Doctor.